Hello everyone, welcome to my channel. So in this video, we will continue our introduction of probability. So in previous videos, we already talked about two important examples of random variable. One is an important example of discrete random variable. It's a binomial distribution. And the other one is an important one for continuous random variable. It's a normal distribution. So here in this video, we want to talk about the relationship between these two distribution. So actually we can use a normal random variable or normal distribution to approximate a binomial distribution. Okay, so first, if you don't review my video of the binomial distribution or normal distribution, please look at it first. And let's see if we say our random variable capital X is a binomial random variable with a parameter n and p. So here p is the probability of the success for each of the Bernoulli trio, and n is how many Bernoulli trios we have in this experiment. So in this situation, the probability mass function is in other words, this is giving us a probability when our capital X equals small x. So this is gives this combination of nx times the probability of p to power x with 1 minus p to power n minus x, right? So this means in the n Bernoulli trios we get x a success result and n minus x unsuccess or failed results. Okay, so now if we want to draw the graph of this PMF, what is the result? So here, if we look at that one, when n, for example, is a really small number, for example, when n is equal 2, then what's the possible value of our x? Then in this question, our x can be equal 0, no success, 1 success, or 2 success, right? So in this case, if you want to draw a graph of this PMF, what we can have this is, for example, if I draw here, so in this case, when we assume the probability or the value of our p is equal 1/2, then what is the value when x equals 0? So by our definition of the PMF, we can get the result is equal 1/4. So this is when x equals 0, we have this is our first point. And when x is equal 1, by our definition of PMF, we can get the value as this one is 1/2. And the last one is 1/4 again. Okay, so now we can have our graph for this at this 3 point. So this is when n is equal 2, and then if we have n is equal 4, and we also have p is equal 1/2, then now the possible value of our x could be 0, 1, 2, 3, 4 until 4. So in this case, if we draw this picture again of our PMF, what we will have? We will have a picture look like. So then the graph of our PMS will be look like this. So in our horizontal x, this is the value of our possible value x of our random variable, and then for this each of them, by our definition of the PMF, we can get this 5 points in our graph. Okay, and then what happens if we increasing the value of our n to much larger results? Then, for example, here what we can have a graph. It's also like first is kind of like when p is equal 1/2, then this one will also symmetric, and then this will also have if the graph to the median of our possible values of this random variable, it will have much higher probability. And on the left tail and right tail, they will have much lower probability to have our random variable equal this value. So when the n become larger or we change the value of our p, this characteristic is still very similar. So it means it's still something with a very high peak in the middle, and then we'll have a much thin tail on the left inside and also right inside. So if we, for example, draw an example when n is really large, so then what we can have, we will have a graph looks similar to this green point. So for this one, it means we have very large n, and now we will also have a high peak for this graph as the middle value of our all possible values of our random variable. And then when this value x become more smaller or more larger compared with our middle value, then we can have the probability is decreasing. So if you look at this one and if you compare this with a bell shape of our normal random variable, you can see when we link all of the green point here, this one could look a little similar to our graph for the bell shape for a normal random variable. Right, so it's like here, if I compare this with the bell shape, we can say it's very close to that one. Okay, so that's why when n is very large, actually we can use the normal random variable to approximate binomial random variable. And why we do this, why we need this approximate. So when we look at the definition of our PMF for a binomial random variable, what will happen if we need to compute when this value when n is really large? We can find this will need a really large computing of our combination. And maybe you will say, okay, we have calculator, I don't worry about when n is large. However, what will happen if you think we compute the probability when we want to compute x is a binomial random variable, and then for this one, if we compute the probability capital X smaller or equal to a number. So for example, if you assume the n here is equal really large number, for example 100, then we know all the possible value of our small x. It could be 0, 1, 2 until 100. And then when we want to compute the probability x smaller or equal to 50, what this means? This means by this probability, we know this is a CDF, the cumulative distribution function of our binomial random variable. So this will equal the probability when x smaller or equal to 50, and the probability of our capital X equal our small x, right? So in other words, this is our x smaller than 50 of our PMF. So in other words, what we have, we need to compute the PMF's value at 0 plus the value at 1 plus the value at 2 and sum up to the value at 50. So in this case, it means we need to compute in total 51 calculations. And all of them is, by the definition, is our n of x and p to power x, 1 minus p to power n minus x. So you will find this is a really annoying computation. Even we have a calculator, it still takes us long time to compute this one, but n is really large. So what we can do is, because in the graph, we know this graph of when n is large, our binomial random variable is really looks similar with a normal random variable. So what we can do is, when n is large enough, so here in this video, I setting this is n times p larger than 5 and n times 1 minus p larger than 5. When we satisfy this requirement, then we can use normal distribution to approximate a binomial distribution with a parameter n and p. And of course, for a normal random variable, we need to know what is a mean and what is a variance. So if you already viewed the video of our binomial random variable, we know the mean of a binomial random variable is n times p, and the variance of a binomial random variable is n times p times 1 minus p. So now when we use the normal random variable to approximate binomial random variable, so it's a very smooth idea of use the same mean of our binomial random variable to set this as our mean for normal random variable, and the same idea for our variance. So here we will use a normal random variable with a mean np and a variance np parentheses 1 minus p to approximate our binomial random variable. Okay, so here when we say approximate binomial random variable, then what this means? This means now we can use the PMF, the PDF of the normal random variable. And the more important is we can use the CDF of our normal random variable to guess the value of the CDF of our binomial random variable. And for a normal random variable, we know it's hard to get an explicit equation of our CDF. However, if the normal random variable is a standard normal random variable, we can use the table of the CDF of a standard normal random variable to compute our binomial CDF of binomial random variable. So the method we will do this because we will need one more important method or tips is continuity corrections. So why this? Because if we think about what is a random variable for a binomial random variable, it's a discrete random variable. However, for the normal random variable, it's continuous. So what's the difference? That means for our binomial random variable, x can only be some integer, 0, 1, 2, 3, and there is no like 1.5, 1.6 for a binomial random variable. However, for a continuous random variable, normal random variable, it could be any decimal number like 1.334 or some other thing. So in this case, if we want to use more information of our normal random variable CDF or PDF, what we generally do is we will use like generally here I use like 0.5 to enlarge a little of our range for our random variable. So for example, if I want to compute a CDF of our binomial random variable at value small x, so that means I want to compute the probability of our capital X smaller or equal to small x. Then we will use this to enlarge it. To enlarge this to probability of our capital X smaller or equal to small x plus 0.5. So when this x is a binomial random variable, of course, this didn't change the value of our probability because capital X can only equal integer. So if this is a smaller or equal to 1 or smaller or equal to 1.5, this is same, right, for the binomial random variable. But then when we want to approximate this to our normal random variables, so that means here I assume this x is be approximated by a normal random variable. So that means I can assume this. Now I change x is a normal random variable with mean as np and variance as np1 minus p. So then to compute a CDF of a normal random variable, what we should do, we should use the standardization of a normal random variable. So in other words, we will minus the mean. Here is a mean equal mean and divided by sigma, small or equal to the value on the right hand side of our small or equal to symbol minus mean divided by sigma. And here, please remember the mu is our mean, is AMP, and then the sigma is our standard deviation, so it's square root of NP1 minus P. Okay, and also if we let capital Z is equal our x minus mu divided by sigma, so this actually is a standard normal random variable. So if you are not familiar with what I write in red color about how to rewrite a normal random variable to a standard normal random variable, please make sure you look at my video about this topic in this channel. Okay, now if we have this one, I can rewrite this as a probability of our capital Z smaller or equal to plus the value of our mean and variance. So this is NP divided by square root of NP 1 minus P. Okay, so this is how we can use the normal random variable to approximate a binomial random variable CDF. So for this equation, now what we can do, we can just use the table of the CDF of a standard normal random variable to find the value of the probability. Okay, and one more thing is here we talk about what we should do when this is a probability capital X smaller or equal to small x. So what should we do if we have an equation of capital X is larger or equal to a small x? So remember I said this continuity correction, it means we want to enlarge our region. So what this means? This means if you think about we have here about the axis, and when we say this is about capital X is a smaller or equal to small x, so it means this is the left part of this axis, and then what is enlarge means for this shadow part, it means we want to add it x plus 0.5 here. So that means this region will become the blue shadowed the blue shadowed part plus the red shadow part. However, if our question is about x is greater or equal to our small x, so that means this will become the right hand side of our small x. And now if we want to enlarge this region, what this means? This means we need to find a point on left of our small x and then add this red shadowed part. So here what we choose small x minus 0.5. Okay, so this, although we always say we need to use the continuity corrections during our approximation of a binomial random variable by normal random variable, this depends on our symbol x greater or equal to or smaller or equal to, and this will decide it when we use this one. We will use x plus 0.5 or x minus 0.5. Okay, so now by the graph we know this means x minus small x minus 0.5. Okay, and then to compute this again we need to have the standardization of this one. So it's a capital Z greater or equal to x minus 0.5 minus our mean and divided by standard deviation. So NP1 minus P square root of this. And now if we want to use the table of our CDF, standard normal random variable, we still want to add about a symbol of the CDF. So it means capital Z is smaller or equal to something. So that means we need to use 1 minus capital Z smaller or equal to the same value. So if for here you feel this is unclear, like why from the previous equation we need to rewrite this as a 1 minus the probability. So you should also look at our question of the probability, like axiom of probability, or how to compute the CDF of probability. So please read or look at my videos in previous one. Okay, And then this is a two case when x smaller or equal to or x is larger or equal to. So before the end of the videos, I want to write the last case. The last case is if x is between two values. So for example, we say this is larger than a and smaller or equal to b. So in this one, what we want to do, you can guess this. So we still want to enlarge this range, right? So that means we want to have the right end point is to more further right, left end point is to more further left, right? So this will means what we want to do is in the graph you can see A and B. We want this become here A and here B. So this will means A minus 0.5 and B plus 0.5. So this is what we want. So that means here in the probability, we will rewrite this as a probability x is greater or equal to x a minus 5.5 and smaller or equal to b plus 0.5. So this is how we can use the continuity corrections to compute the value of CDF for our binomial random variable by the continuity and approximation of normal random variable. So this is my topics of these videos. So in next videos, I want to continue talk about some important example of continuous random variable. So please subscribe my channel and see you in next video.